our next topic is magnetism. So with magnetism, we are going to break this into a couple of different pieces. The first thing we're going to look at are the magnetic fields themselves and how those magnetic fields affect the motion of objects. Then we are going to come back and we are going to take a look at what is actually causing those fields in more physics detail. Then we will look at uniting kind of concepts of electricity and magnetism. So here's the basics. So we have magnets. There are naturally magnetic materials, and there are magnets that exist in nature. That's how we discovered magnetic fields. And we assumed that our magnets have north and south poles that kind of act a little bit like electric charges. So opposite poles are going to attract, like poles are going to repel. So our magnets can have lots of different orientations with those. So we have the north side and the south side of these magnets. Now, there are going to be some similarities and there are going to be some differences. So I do have to caution you to make sure that things that we learn about magnetic fields, you don't go back and confuse with electric fields later on. The biggest difference is that with charges, we can have isolated positive or negative charge. I can have an electron, which has a negative charge. I can, on its own, have a proton that has a positive charge. But there is no such thing as a magnetic monopole, where you can have just an isolated north or south pole. They've kind of theorized about them and come up with kind of lab simulations where they think it might be possible, but they've never actually been able to make a monopole yet. And there's reasons for that. So these magnetic monopoles don't exist. So you can never have just a north or just a south. If you were to take a magnet and you were to break it up, and this doesn't ever work anymore. So if I had this magnet that had a north pole and a south pole, and I was to cut it, what ends up happening is you get two magnets, both with a north pole and a south pole. No matter how many times you chop it up, you can never get that single pole. And this is going to have to do with how magnetic fields are actually created within an atom. The Earth itself has a magnetic field with poles that are located near the geographic poles. It's just weird because they're opposite. So we know that our north geographic pole is up here and, somewhere in the Arctic Circle. And we know that our south geographic pole is down there. But the actual magnetic axis is tilted. And it changes, the tilt changes, I think it's around 7 degrees on average, but it does change. And the other big thing is the Earth's south magnetic pole is actually near the north geographic pole. And the actual north magnetic pole is near the south geographic pole. So it's actually flip-flopped. So we can see that magnetic field lines are going to leave the north pole of a magnet and come in towards the south pole. So the north pole's kind of like our positive and the south pole's kind of like our negative. So what happens is the needle of our compass is a magnet. And so what happens is the north pole of the magnet, of the compass, the north compass points south towards south magnetic pole. So that's why we have determined that that is our north direction, because that's the north side of our compass. So it's actually backwards. And so you just have to make sure that you just don't get those confused. If you've actually ever done any orienteering, like in Scouts, or if you've gone geocaching or anything like that, you do have to be careful that the map directions and your compass don't actually line up. And if you're only going for a short walk, not accounting for that's probably not going to get you too lost. But if you're going on, a several-hour hike or a multi-day hike, the longer and further you hike, the bigger the deviation between what your map says is north and what your compass says is north. So if you don't have a compass that can adjust for that, you will get off track. So these electric field lines, magnetic field lines for the bar magnet look kind of like the electric field lines for a dipole, so there are some similarities that we have for those. So looking a little bit more at those magnetic fields, if you take a look at the magnetic field of a bar magnet, we can actually visualize these with iron filings. You might have played around with those like in elementary school, or if you've ever used an Etch-a-Sketch. Etch-a-Sketch basically uses magnets and electric fields to like draw things. So what happens is the magnetic fields, I'm going to get electric and magnetic field confused sometimes, so I'll try and always catch myself there, but always leave the North Pole and wrap back in towards the South Pole. So they leave north and south. And you can see that you can trace those out in these different field lines with those magnets. And if we were doing a physical lab, we would actually be breaking out the magnets. And you would actually get to see those iron filings do their thing. So the Earth does not have a bar magnet inside of it. However, the Earth has an iron-nickel core at the center, and that iron-nickel core is actually rotating. And the rotation of that iron-nickel core, it's actually the molten parts of the iron-nickel core in the outer core, is what we believe is responsible for our magnetic field. And that's rotations create a magnetic field that looks very similar to a bar magnet, which is why we sometimes represent Earth's magnetic source as that bar magnet, just to visualize it. But it's really due to that rotation. If the core of the Earth stopped rotating, we would not have a magnetic field. And that magnetic field does a lot of really cool things for us. It helps to protect us from the solar wind. If we didn't have that magnetic field, we would have basically be scorched and we wouldn't be living here. So we use the symbol capital B for the magnetic field, and for the life of me, I've never researched why. So that's a capital B. It is a vector, so it's represented with the arrow symbol for the vector. Outside of the magnet, when you're outside of the magnet, the magnetic field lines always point away from the North Poles and towards the South Pole. Actually, inside, these magnetic fields actually continue to loop. And so when you're inside the magnet, those field lines do actually make continuous loops. That's a difference from electric fields. Electric fields can never enter like the conductor. In this case, we do get magnetic fields inside of magnets, and they actually point the opposite direction from south to north inside. The SI unit for the magnetic field is the Tesla. A Tesla is equivalent to 1 kilogram per coulomb times seconds. Sometimes you might see Gauss used in different problems. 1 Gauss is 10 to the negative 4th Teslas. So Earth's magnetic field is actually really, really small in terms of Teslas, about 0.00005 Teslas. Although it's super important to protecting us, it's really, really small. A permanent magnet, like you might find in your headphones, might be 0.1 Teslas, so a little bit bigger. A big electromagnet like you might see for industrial uses might be 2.6 Teslas. Our superconductor magnets can be around 10 Teslas. When you start getting to magnetic field strengths that are that large, you have to make sure you are not wearing anything magnetic, because those are so strong that they could cause you to not be able to move your arms away from the magnet. If you're wearing something like that, very, very dangerous for that. People can get injured with wearing magnetic materials near magnets that are that strong. So where does this magnetic property actually come from? Now, this is going to be an oversimplification, because in order to really understand what's going on, you have to know a lot more, not even really, but to get a better understanding of it, you have to understand quantum mechanics. And you have to start talking about the angular momentum and so forth. So this is going to be a simplification of what's going on. If you do take a quantum mechanics course, either through chemistry or physics, you will learn a little bit more about this. It's kind of cool. So from our very simplified understanding of what we would picture is, if you picture atoms, they have electrons inside. And you might have heard in chemistry about electron spin, that some electrons are spinning one way and other electrons are spinning other ways. We represent that spin usually with an arrow. So you have arrows that are going from in opposite directions. If you curl your fingers in the direction of the spin, the direction your thumb points is actually where because you're inside the field, you're going from like north to south kind of with that. Those exact orientations, like said, are approximate. So we call one spin sometimes represented with a positive 1/2 and the other one with a negative 1/2. That's that magnetic spin number. It's one of your the quantum mechanic properties that you might have used when you talk about orbitals. And with this, they're not actually spinning, but they do have angular momentum. So you could have, if you remember from your mechanics course, if they taught that, your angular momentum of a moving charged particle is R cross P. So that objects moving even in a straight line relative to some axis of rotation, such as the center of an atom, can have angular momentum. So it's possible to have angular momentum in one direction. You could have angular momentum in an opposing direction. And that's where this like spin coming from. It's not really from because they're actually sitting there spinning in opposite directions, but they have angular momentums that have components that are perpendicular to each other. So one might have an angular momentum vector that way. The other one might have an angular momentum vector that way. They have some components that are opposite to each other, and so therefore they will attract. So the idea that these electrons are being able to attract to each other, even though their electric fields are repelling, because electrons are obviously creating a repulsive effect. Their different angular momentums creating this spin creates magnetic fields, and those magnetic fields are in opposite directions. So then essentially the south and north poles of those magnets, those little mini electron magnets, are attracting to each other. And once again, they're not holding hands like you might have seen in chemistry, so you don't have electrons actually paired, around your atom, traveling in orbitals together like that. Basically what happens is one electron's moving this way, another electron's moving this way, and they're kind of spend proportionally more time kind of in each other's orbit, essentially. I guess you could say kind of like little mini orbits around kind of their motion of the atom. So we use that idea of kind of magnetic fields and this picture of spin to kind of simplify down this really complicated motion of these electrons to understand this idea of this magnetic field. So you can, for simplicity, picture that some electrons are spinning one way, represented with an up arrow, and some are spinning the opposite way, and those create magnetic fields that attract. So while they're not actually spinning, basically these paired electrons are creating magnetic fields that will be equal and opposite, and so they cancel out. If you have a material that has any unpaired electrons, those will create a net magnetic field. So for example, you might have seen orbital notation in your chemistry class. When you fill orbitals, you fill them with up arrows first, and then when you run out of arrows, you come back and pair. So this example is for an atom with 7 electrons. So this is actually nitrogen. This is a single individual nitrogen atom. Now we know that nitrogen atoms don't actually occur in nature by themselves. They like to be paired. They're diatomic. But if you did have an individual nitrogen atom, it has these 3 unpaired electrons. So those have similar magnetic fields. So the magnetic fields of each of these unpaired electrons would add to create a net magnetic field. As soon as you pair up those nitrogens, those unpaired electrons, if you were to picture the other nitrogen, you'd have a 1s, and it'd have an up and a down, and it would have a 2s, and it would have an up and a down. And then what would happen is those 3 unpaired ones this other one have, these come over and they pair with this one, and that's how they actually form their bond. And then there are no longer any unpaired electrons because these are now used up. So then diatomic nitrogen, N2, would not be magnetic because it doesn't have any unpaired electrons. So our traditionally magnetic materials are going to be those that have quite a few unpaired electrons in their electron configuration. So for example, iron. Iron usually has an unpaired electron. So when you take into account all of the electron configurations, we can represent what we call a magnetic moment as the net magnetic field of that material. So each of these arrows here is going to represent one atom of a magnetic material. So each atom is going to be vibrating, and it might be in a different orientation. So if we have a magnetic material, which is a material with unpaired electrons, and it is currently unmagnetized, that's because its little dipole moments, its little north sides of the magnets, are pointing in all sorts of random directions. However, if we can align all of those little magnetic moments, then what you get is a magnet. So we have the electric field is kind of leaving the north side, coming towards the south side, right? So this represents a whole bunch of little baby magnets. North side, south side, north side, south side, north side, south side, north side, south side. So that the net result is this magnetic field. In this case, all of those are in all sorts of different directions, and they're going to cancel out. Now, temporary magnets, so something like if you take an iron nail and you run it through a magnetic field, essentially what you're doing is by running a magnetic field over this, by like taking a magnet, and you can do this. If you have a magnet, you can take an iron nail, you can take a paper clip, and you can move it over and over and over again. What that does is that actually aligns all of these little dipoles and then creates a magnetic material. Now they're called temporary because those atoms are vibrating, and if you don't keep them in a field, or if you drop them too many times, anything you do that allows the atoms to vibrate more, they will eventually return back to their demagnetized state. Whereas you can have permanent magnets that hold that state all the time. So why does cutting a magnet in half result in two new magnets? Why can't you create separate poles? Well, this diagram shows that. Because if I was to create a cut right here, what ends up happening is I've got a north side and I've got a south side. And then I've got a north side and a south side. So I've now created two magnets that have a north side and a south side. If I was to do that again, if I was to cut here, that's going to give me a north side and a south side. So I now have a north, a south, a north, a south, a north, south side. I have three magnets. Now we could keep doing this, but I can't cut here. Why can't I cut there? Because that would be cutting up an electron. Basically, you can't do that in terms of being able to create those magnetic monopoles. So your electrons are always going to be spinning. We can't cut up our electrons. So therefore, we have spinning magnets. Now, when you start getting what's below a magnet, electron, you start talking about like quarks and things. It gets weird and funky. So we're not going to worry about that. But that's why they think that theoretically it's possible that there might be a magnetic monopole out there somewhere, that it might be possible to do it. They've tried to come up with simulations to do that. But for our purposes, since we are looking at, the non-quantum scale, it is absolutely impossible to have a magnetic monopole, because cutting it up is just going to give you smaller magnets with two poles. So now we're going to take a look at how existing magnetic fields influence the motion of charged particles. So this is going to be our first equation. So we have the magnetic force is equal to the charge of our particle times the velocity of the particle crossed with the magnetic field. So that is not a multiplication sign. That is a vector cross product. So you've seen vector cross products hopefully in your mechanics course. We saw them briefly with the electric fields of dipoles. but we're going to see cross products a lot more heavily here in this unit. So looking at this, our capital F with the arrows, the vector force on the particle. V is the velocity of the charged particle. Direction matters because it's a vector. And capital B is our magnetic field vector. So just taking a look at this equation without even considering what is meant by that cross product, what is the force if the charged particle is at rest? Well, since the cross product is kind of like a fancy way to multiply, anything times 0 is 0, so there is no force on a charged particle at rest. So magnetic fields do nothing to charged particles at rest, but they will have an effect on moving charged particles. So breaking this down a little more, the force is proportional to Q, which must include the sign of Q. So that means that the force on positive and negative charges are going to be in opposite directions. So if I put an electron into a magnetic field and I have a proton moving with the same velocity in the same direction, its force is going to be in the opposite direction. So we do have to be careful with that sign. The force is directly proportional to the magnetic field, directly proportional to the velocity. The cross product is all about finding components that are perpendicular to each other. So if the magnetic field vector B and the velocity vector V are parallel to each other, then you aren't going to have a force. So if B and V are parallel or anti-parallel, your force is going to be 0. There will be no force. As long as they are not parallel, then the resulting force is going to be perpendicular to both of them. So if I was to have my velocity in one direction and my magnetic field in another direction, I know that my magnetic field is going to have to be, my magnetic force is going to have to be perpendicular to both of those. So you always end up with a three-dimensional vector resultant because you have to be perpendicular to both. And you're going to have to find the direction according to the right-hand rule. So, because this is a voiceover recording, I cannot show you what my hands are doing when I am solving problems. So I do suggest that you pause this video right now and go over and find my cross product right-hand rules example video. It's pretty short, but it reviews how I do the right-hand rule for vector products. I give you a general example, which is any vectors, and then I give an example with torque, and then I give an example with this equation. So you can see what I do that. So I'm going to talk about what direction my hands are pointing. I'm going to try and draw those for you on the diagram here as I'm working, but taking a look at that video will help. There are other ways to do right-hand rules. So what I say may not agree with what you see for the right-hand rules from any of the other YouTube videos that I give you in the tutorials or what you may find online. So if you don't like the way I do right-hand rules and you like the way you've seen it somewhere better, go for it, because there are so many different ways to do that. I do the right-hand rule the way I do because it is one rule for every cross product. You may see that in a lot of physics videos, they're referring to the Fleming's left-hand rule, or this right-hand rule, or this curling, I don't know what rule. There's a whole bunch of them. I use one cross-product right-hand rule, and I use one curling right-hand rule. So I've simplified a lot of the hand rules that are in physics down to basically 2. So that's why I do what I do. So when you're done watching that video, I would come back here and join back in. So since we are going to be looking at vectors in 3 dimensions, we can of course have magnetic field vectors that are like to the right, up, towards the top of the page. I use top of page, to the right, to the left, and towards the bottom of the page. Try to avoid up and down, because I don't know what up and down are necessarily. Are you talking about up out of the page? Are you talking about up towards the top of the page? And then for into and out of, sometimes you see these represented with circles as well. when you have an X into the page, that represents into the page. Picture an arrow. If you had a fletching, if you had like an arrowhead here, and then you had the fletching for the arrow. If you were to look at the arrow dead on, the very first thing you would encounter is a point. So if this arrow was pointing towards you, the point would hit you first. If you were looking at it from the end, you would see the fletching first. So if this arrow was pointed into the page, the back end of that arrow would be at your eye, and you would see the X from the fletching. Technically, you always see both, but that's what would hit your eye first, essentially, would be that X. Whereas if you were looking at the very tip of the arrow because it was pointed up at you, the tip of the arrow is what would be reaching your eye first. So that's how we do into the page and out of the page. So top of page, bottom of page, right, left, into the page, out of the page. I do not want to see up or down in any of your descriptions of vector directions. Please avoid it. So the 2D cross product, as long as your vectors are in like the XY plane or the YZ plane, and you're not like it in like an I hat, J hat, K hat, where you have components in all three directions, the cross product simplifies down to either F equals QVB sine theta, or QV perpendicular B, or QV perpendicular B. So there's different ways to do that. I prefer these versions rather than the version actually with the sine theta. The only way that works is if you're given a velocity and you're given the magnetic field and this is theta. So if the angle they give you between them is theta, you can use sine, but sometimes they might give you different angles. Like they might do something like this if they give you that theta, or if they give you this theta. That's not going to give you the exact right answer. The theta would work is the one that goes directly between those. So you do have to be careful when using sine theta because the angles they give you in the problem may not match that definition of theta as being the angle in between the vectors. However, the perpendicular component of the velocity to the magnetic field or the perpendicular component of the magnetic field to the velocity work no matter what angle they give you with those definitions. So take a little bit of practice right here. Like I said, it's a little hard to look at the directions, but what do we mean by these equations? So if I have a plane, so let's assume that this is the XY plane. So V and B are both in the XY plane. Then if I wanted to find V perpendicular to B, what I would have to do is I would need to take a 90-degree angle and off of B, and then I have a right triangle. And so V perpendicular would be the opposite side of this right triangle where V is the hypotenuse. So that would equal V sine theta. On the other hand, if I wanted to use the definition QVB perpendicular, what I would do is I need to find the component of B that is perpendicular to V. So that would be creating a triangle here where that is a 90-degree angle, where B is the hypotenuse and B perpendicular is the opposite side of that right triangle. So B perpendicular would be B sine theta. So then in both cases, you get the QVB sine theta in this example. But where does the force vector point? So this is where you would use the right-hand rule. So these are both the same diagram. So what I would do is I would point my fingers in the direction of V. So I'm going to take my hand and I'm going to straighten it out, and I'm going to point my whole hand to the right of the page. And then that B is kind of up towards the top of the page. So I'm going to rotate my palm so that it is facing the top of the page while keeping my fingers pointed straight to the right. What that does is that points my thumb up out of the page. So that would create a force that is up out of the page. So that would point up out of the page, which I could kind of drew like that. So that would be perpendicular to both. That would be out of the page for that one. So here's that summary of what I just did. So my right hand rule, I start with my fingers fully together and fully extended, so as straight as they can be with my thumb at a right angle. I point my fingers in the direction of the first vector, in this case V. I rotate my hand until my palm points in the direction of B through the shortest distance, the shortest angle rotating. And then your thumb points in the direction of F. So here they've got velocity to the right, and they've got B coming up out of the page, so the person's hand is facing up towards the ceiling, and then their thumb is kind of pointed down towards the bottom of the page. Now, because our equation is QV cross B, you might have noticed on the previous example they put the absolute value signs. So to find the magnitude, you look at the absolute value, but the sign matters. So if you are doing the right-hand rule, you do the right-hand rule for a positive charge. You can either do the right-hand rule for the positive charge and flip the sign, so out of the page becomes into the page with the negative charge, or you can use your left-hand rule. So you can use your left hand for a negative charge, or you could always use your right hand and flip the sign so it's in the exact opposite direction for the negative charge. So here's a couple of examples. So this first one right here was one that we just looked at. So we had our velocity to the right. So you point your fingers to the right, you rotate your palm towards the top of the page, and then your thumb would come out perpendicular to both of those. For me, that points up out of the page. That's kind of what they're trying to represent in this kind of skewed perspective drawing. If this was a negative charge instead, your force would be in the exact opposite direction. So you could do that with your left hand. You could point your fingers directly to the right with your whole hand straight. I'd rotate my palm to face towards the top. That forces my thumb down into the page. There's some similar examples kind of here showing you that those forces would end up coming the opposite directions depending on whether you have a positive or a negative charge. So if you look at this one right here, this one we have a negative charge, so I'm going to use my left hand and I'm going to point my fingers kind of diagonally in that direction of V on my screen. And then I'm going to rotate my palm towards the bottom of my screen because that's where B is. It's towards the bottom. And now my thumb points out of the page with my left hand. So that is going to be my force on that one. All right. So now that we know the direction of the force, how do these electrons actually move? So here's an example. We have an electron traveling at 2 times 10 to the 7th meters per second in a plane perpendicular to a 0.01 Tesla magnetic field, and we want to describe its path. So let's picture this. Let's picture that our magnetic field is pointing out of the page. We have an electron, and let's assume that at one instant in time, that electron is moving towards the bottom of the page. So we want to figure out what's happening to its path. Well, if I want to figure out what's going on, I need to figure out where the force is. So I would use, with my electron, my left hand rule, well, my right hand rule, or flip the sign, or my left hand. So in this case, I'm going to point my fingers down towards the bottom of my page. So that's my fingers down towards the bottom of my page. I need to rotate my hand so my palm is up out of the page with my magnetic field. So my palm is pointing towards the ceiling. And then I can see that my thumb points to the right. So I have a magnetic force that is perpendicular to my velocity. Now, puzzle me this. When did you see this in your mechanics course? What type of motion did you have when your force was perpendicular to the velocity? You had uniform circular motion. So the magnetic force would act like a centripetal force if when that electron is moving, the force is perpendicular to the velocity. Well, we know it's perpendicular at that instant, but what happens as it moves? So you can see that if you were to pick any section around the circle, as that starts to move, that force is always going to be end up pointing perpendicular in towards the center of that circle. So if I pick this one that I drew right here, my fingers would point down and to the right. My palm would have to rotate up, so that forces my thumb to be towards the left. If I pick this spot on the bottom, same idea. So these electrons and protons, when they are put into magnetic fields, are going to rotate in circular motion. It's kind of fun. Now, the acceleration is only going to be radial or centripetal. There will be no tangential component. So you will have no change in speed. You can only have changes in speed if you have at least some component of your force in the direction of motion. So there's no component of force in the direction of velocity. There never will be. So magnetic forces can never cause changes in the magnitude of the velocity. It can only cause a change in direction. So charged particles will always move in circles with a constant speed. Our centripetal acceleration is v squared over r. If you don't have that memorized, it is on your formula sheet. And then r is going to be the radius of the circle for that. So how would we find the radius of the circular path? Well, we have to use uniform circular motion. So mechanics, it just doesn't go away. So what we would do is we would assume that the magnetic force is equal to the centripetal force. So I'm going to set FB, which is my magnetic force, equal to centripetal force. I'm just looking at the magnitude right now. The direction is determined by my right-hand rules for positive and negative charges. So I'm just looking at the magnitudes. And then because in this example, V was perpendicular to B, then I can just do QVB. And then my centripetal force is M times AC, and my AC is V squared over R. So if you were going to make this simplification from QV cross B to QVB, please make sure that you state your assumptions when working problems. Please don't just write QVB. Please write the assumption that it's because those vectors are perpendicular to each other. So then if you rearrange and solve for R, you end up with one of the V's canceling out. So you end up with MV on top here, and QB on the left with R on the bottom. So solving for R, you get MV over QB. Now MV, we've seen this before. This is momentum. So the radius is proportional to the momentum. So the larger the momentum, the bigger the radius is going to be. So the larger the mass, the larger velocity. And then it's inversely proportional to charge. So the larger the charge, the smaller the radius is going to be. So larger charges are going to have tighter circles because they're going to be more strongly influenced by the magnetic field. And of course, the stronger the magnetic field, the smaller the radius, and so therefore, once again, the tighter the circle. So more charge, more magnetic field, tighter circle, more momentum, more mass, more velocity, the bigger your circle is going to be. So what we can do is we can work a practice problem. So in this case, we have the magnetic field of the Earth at a certain location is directed vertically downward. By the way, this is going to most likely occur at the north, near the North Pole, up in the Arctic Circle area. That's when we're going to have a magnetic field pointed directly downward. And it is going to have a magnitude of 50.0 microteslas. Remember, the teslas are very small, so you're going to tend to see some of those smaller SI units. And we have a proton that is moving horizontally towards the west in this field with a speed of 6.0 times 10 to the 6 meters per second. So there's different ways to visualize this. I'm going to represent vertically downward as into the page. So I'm doing into the page. is equal to downward. And then that is where my magnetic field is pointing. And then I know that my charged particle is moving towards the west. So then I'm going to find north, south, east, and west. So I'm going to have a charged particle. In this case, it's a proton. Is moving west with a speed of v equal to 6.20 times 10 to the 6 meters per second. I want to find the direction and magnitude of the magnetic force the field exerts on this charge. So for the direction, this is a positive charge, so I'm going to use my right hand. I know that my magnetic force is QV cross B. So if I point my right hand with my fingers directly to the left, I need to rotate my palm so that it is into the page with the magnetic field. I get that my force, my thumb points down towards the bottom of the page. That towards the bottom of the page is in the southward direction. So the direction of that magnetic force is going to be south. Now because into the page and my west are going to be perpendicular to each other, I can state that my velocity is perpendicular to my magnetic field, so that my force is magnitude is just going to be QVB. And then I am looking for the magnitude of that force, so I would plug in the charge. It's a proton, so Q is going to be 1.6 times 10 to the negative 19th coulombs. My speed is going to be 6.20 times 10 to the 6th meters per second. And then I'm going to have, I ran out of room. This is going to be 50.0 times 10 to the negative 6 Teslas for the micro, converting there. And if you plug in those values, you should get that the magnitude of the force is about 4.96 times 10 to the negative 17th newtons. So that's a very, very small force, and it is directed to the south. So then the next thing I want to do is I want to find the radius of the circular arc followed by this proton. So anytime you're doing this, you need to solve for the radius. The equation for the radius that I showed you before is not on the formula sheet. If you memorize it, good, but you will not get full credit for problems on tests if you do not show the derivation, because you have to start at the equations that are on the formula sheet. And we can do that our centripetal force is equal to our magnetic force. So I'm going to walk through this again. Our centripetal force is going to be MAC, or mv squared over r. The v squared over r is on your formula sheet. And then our FB is going to be QVB. So one of our v's are going to cancel. So solving for r is going to give us mv over q times b. So you would then plug in. So our mass of a proton is 1.67 times 10 to the negative 27th kilograms on the formula sheet. Our velocity is going to be 6.20 times 10 to the 6 meters per second. The charge is going to be 1.6 times 10 to the negative 19th coulombs. And our magnetic field strength is going to be the 50.0 times 10 to the negative 6 Teslas. I get that my radius is about 1,294 meters. I think down here they just put it into kilometers. So there you go. So once again, show your assumptions. You have to derive that equation for the radius of the circle. Even if you do it 6 times, you'll have it memorized. You'll be able to do it fast. Now, if the velocity of the particle is exactly perpendicular to the magnetic field, then we're going to get that perfect circle. But what if you have a little variation in that? What if you give a little kick to the speed? The radius is going to get bigger. which is how we create a cyclotron. So here is an example how a cyclotron works. The kick is going to be created by an electric potential difference. So what we end up with is, in the cyclotron, we have two magnets. So this is going to be a magnet, and this is going to be a magnet. And we're going to assume that these magnets have a uniform magnetic field. Now we're going to assume that we have electrons that are being emitted from a source. So we have our initial source of our electrons right here. Well, to get our electrons to even move, we need to accelerate them. Magnetic fields can cause a change in direction, but not a change in speed. So if I want my electron to move and even speed up, I need to apply an electric field. So what they do is they apply an electric field by creating a potential difference between those two sides of the cyclotron, so that we can accelerate and get our electron moving with some sort of initial velocity v, so that it is going to enter this magnetic field with a speed of v. Now these are electrons, so we know that electrons move in the opposite directions of the electric field. So I'm actually at the start going to have an electric field that is pointed from the top to the bottom of that cyclotron right there. And that's going to cause my electron to speed up and exert a force in the opposite direction of the electric field. So that's going to be created with a square wave. And we're going to see why that's actually created by a square wave in a sec. So once we have that velocity as this enters here, we know this is an electron. So I'm going to use my left hand, and I can see that these electrons are all curving towards the right. So if I put my thumb towards the right, because I know that's where the magnetic force has to be on that electron, and I put my fingers towards the velocity up at the top, I can see that my palm of my hand has to point into the page. So the magnetic field in this one has to be into the page. So I have a magnetic field into the page. So that magnetic field is only going to cause my electron to curve. So it's going to curve and keep a constant radius curve right here. And then if my electron was experiencing force upward here, I now want to accelerate it to get it faster. So now I'm going to have to switch the direction of the electric field. So if I switch the direction of my electric field, my electron is now going to experience a force towards the bottom, and it's going to speed up. So now it's going to be moving even faster. It's going to have a faster velocity. So now it's going to create an even bigger radius circle. So you can see this next half circle here is even larger than the original one. Now, what direction is the magnetic field in that section, in this bottom half? Well, if I put my fingers towards the bottom of the page, my magnetic force is now curving it to the left. So with my left hand, that is going to keep my magnetic field also into the page on that side as well. So then it's going to curve around, and now my potential is going to switch directions. So basically, if you picture that square wave, so if here's my electric field or my potential, I'm going from positive, flipping to negative, flipping to positive, flipping to negative. Cyclotron frequency is going to help determine how many times we have to switch and what the rate of that square wave is. So as it goes through, it's going to turn and then get faster in the electric field. Turn in the magnetic field, get faster in the electric field. Turn in the magnetic field, get faster in the electric field. And that is our cyclotron. So if you had a proton instead of an electron, you would get the exact same motion, but just in the opposite direction. You would have the same equation. Now, looking at a proton compared to an electron, they're going to have the same magnitude of charge, but they're going to have different masses. So you're going to end up with a different radius for a proton versus an electron, plus the direction is going to be different. In addition to working with the radius, we might also be interested in the period and the frequency. So different ways to kind of work with those values. So the period in uniform circular motion is going to be related to that circular path. So if our speed is constant, that we can define our speed as distance over time. So the distance traveled by, say, the proton in this circle is going to be 2 pi r, and that speed is v. So if you were to sub in our definition of r over there for that, what you would find is that the period is 2 pi m over q times b. So this is a really nice definition of period because it doesn't involve the speed, so you don't have to know the speed of the charges, but it shows you that the period is dependent on mass, charge, and magnetic field strength. So the bigger the mass, the longer it's going to take to go around, and then the bigger the charge, the magnetic field, the shorter time it's going to take to go around. To find that cyclotron frequency, your frequency is just 1 over the period, so you flip that upside down. So frequency is going to be the rate at which it, the number of times that it goes around in a second. So in that case, you can see that you're going to have a higher frequency rate. It's going to go faster through its rotations if you have a larger charge, a larger magnetic field, or a smaller mass. So if you were to put a proton into a cyclotron, because it has the same charge into the same magnetic field but a larger mass, the frequency of the proton's oscillation is going to be smaller than that of the electron. So you can get the electron to speed up faster than you can with that proton. Some other things that you might be asked to find, you can derive and solve for the velocity. For a particular radius, you could solve for angular frequency, because remember that our angular frequency is 2 pi times our regular frequency. And then, of course, we've got our period there. So these questions can ask you all sorts of things related to that rotation and that oscillation. Now, what if you have a particle that is not moving just perpendicular? What if I have a particle that has components to velocity that are both perpendicular and parallel? Well, what's going to happen is the perpendicular component is going to cause a change in direction, while at the same time, the parallel component is completely unaffected. So if, for example, I have this magnetic field going up towards the top, but my velocity is going kind of down at an angle, so the portion of that that's parallel is going to keep the proton moving down, but the component that is perpendicular is going to keep this thing going in a circle. So when you combine those two motions together, you get a helical path. So you get a helix. So it's going to kind of spiral down towards the bottom there. You won't have to solve problems that involve that motion. It's just kind of cool. So this effect can cause things like a magnetic bottle. So if you have magnetic fields that are being generated by coils of wire that have currents running through them, we'll see how that happens in our following unit. What ends up happening is this spiral effect causes the charged particles to get trapped inside of that field. And so the particles will actually spiral back and forth, kind of in and out, but they won't be able to escape. So you can actually trap your charged particles in a field like that. And this is actually how we get the aurora. So the northern lights or the southern lights are created because of the shape of the magnetic fields. So we have our magnetic fields come out of the South Pole and go towards the North Pole. Because remember, our magnetic north is down there. Our magnetic south is up there. And this cool, different kind of shape where the magnetic fields are weaker in the center is what you end up with in these lobes of what we call the Van Allen radiation belts. And that traps the charged particles in there. And as those particles get sucked down in towards the edges there, that magnetic field gets stronger in strength and actually causes the electrons to energize and causes them to jump up in energy. And as they jump up in energy and then fall back down in their orbits, in their orbitals, that's where we get light to be emitted. And so the different colors of the aurora are based on the amount of energy that is released as those electrons fall back down towards their lower energy states. So let's take a look at another example problem. So here we have a proton moving in a circular path, is perpendicular to a constant magnetic field. It takes 1.00 microseconds to complete one revolution, and we want to determine the magnetic field that is causing that circular path. So what we would assume is that I don't have anything that's other than what's on the formula sheet. So I would say, okay, well, I have my centripetal force is equal to my magnetic force. I'm going to assume that because it's going in a circular path, that my velocity is perpendicular to magnetic field. It also says that here. The right side of this can be simplified to QVB. The left side, the centripetal force, is mv squared over r. So I have a v cancel out. So I get mv over r is equal to q times b. Now, I know in this case 1.00 microseconds to complete one revolution. That is giving my period. So I know my period. So I know that speed is distance over time in a circle is going to be 2 pi r over my period. So I can take that 2 pi r over my period and substitute it in over here for v. So I get m times 2 pi r over the period over r is equal to q times v. I don't like having that r over there in the denominator, so I'm going to multiply it over and get m 2 pi r over period is equal to qb times r. That's just a lot easier for me to see. And now I can see that that radius actually cancels out. And I end up with m2 pi over period is equal to q times b. I am looking for b, so that gives me that b is equal to 2 pi times m over q times t. So I know my period. And I know that this is a proton. So I get that B is going to be 2 pi times the mass of my proton, which is 1.67 times 10 to the negative 27th kilograms, divided by charge, which is 1.6 times 10 to the negative 19th coulombs, times my period, which is going to be 1.00 times 10 to the negative 6th seconds, converting to SI units. And I get that my magnetic field strength is 0.0656 Teslas. So that's an example of how you would solve that. So once again, you have to work within the limitations of what is given on the formula sheet. All right, so our next example is going to be a velocity selector. So this is a type of problem that shows up a lot on homework and test problems. So a velocity selector is a particular device used in experimentation to make sure that the electrons that exit the device have a known velocity. Because if I'm going to work problems where I'm trying to figure out what's happening to a charged particle, I have to know those velocities. But if I have a source of electrons or charged particles or protons or whatever it is, kinetic molecular theory tells me that those charged particles are going to be moving at a whole bunch of different velocities. So how do I get, instead of an average velocity of all those particles, how do I get charged particles of one particular velocity? Well, what I have to do is I have to use crossed magnetic and electric fields. So picture what's going on here. I have on one side a positive plate. On the other side, I have a negative plate. So this is parallel plates. So these parallel plates are creating an electric field from positive to negative. So that's the first part of my velocity selector. The second part of my velocity selector is the magnetic fields. In this case, I have a magnetic field in that entire area that is pointing into the page. So I know that my electrons, actually these are protons in this example, sorry, have a velocity. And that moving charges are going to be affected by magnetic fields, and all charges are going to be affected by electric fields. So I know that I'm going to have both effects acting at the same time. So if I look at this example, in terms of the electric field, once I have my proton has entered my electric field, it's going to experience an electric force that is to the left, because my proton would have that force from positive to negative. Now, on the other hand, using my right hand rule, if I put my fingers towards the bottom of the page in the direction of that velocity, using QV cross B, then my thumb has to point to the right in order for that magnetic field into the page. So what's going to happen is I'm going to have these two competing forces. The electric force is trying to force my positive charge to the left. The magnetic force is trying to force my positive charge to the right. So if I want my particles not to curve, I want them to go in a straight line through the source, then that means that my electric force has to equal my magnetic force. If that's not true, these particles are going to curve. Now, these velocity selectors are often long enough so that basically the only particles that are going to be able to exit are going to have one particular speed. Everything else will have hit the sides before that point. So they make sure that they're long enough to make sure that all these curves pass that are not perfectly straight will result in collision. So only the ones that have that perfect magic speed will exit. So looking here at this example, we have a positive charge moving to the right. We have our electric field going from bottom to top. And our magnetic field is pointing out of the page. So our electric force is going to point on our proton from top to bottom. Our magnetic force, using our right hand rule, is going to point from top to bottom. Now, we know that our electric force is Q times E, and our magnetic force is QV cross B. Once again, our velocity and our magnetic field are perpendicular to each other, so we can simplify that down as QVB. And then we have QE for our electric field. So the charges cancel, so we get that E is equal to V times B. So that solves, and we find that the speed that those charged particles have to move is going to occur based on the ratio of the electric to the magnetic field. So if I want a particular velocity out, all I have to do is adjust the electric and magnetic fields until they give me that perfect velocity. So these velocity selectors are often paired with mass spectrometers. So mass spectrometers are used in chemistry and biology and all sorts of different types of sciences in order to determine the unknown compounds. So in particular, the mass spectrometer that we're going to look at would be able to find the mass of an ionized particle. So you're going to have some sort of source that is going to produce ions. So you'll have some energy that's going to rip away an electron from an atom, and that's going to produce a positive charge. What we have is in this section right here, we are going to accelerate that charged particle. Now, this section of the mass spectrometer is often paired with a velocity selector to make sure that only particles with known velocities enter this magnetic field over here on the right. In this case, we just have some sort of potential difference that is going to be creating an electric field. That electric field is going to go from the positive side over here to the negative side. So our electric field is going in that direction. So we're going to assume that our positively charged particle here starts at rest and then is going to experience an electric force to the right that's going to give it this speed that it uses when it enters right there. And then we're going to assume that the electric field stops here. So that there's no electric field, there's only a magnetic field when it enters that blue box. Okay. So then if we have that positive particle, and we look at our right-hand rule, since my fingers are going to the right, my palm rotates out of the page, my thumb points down towards the bottom of the page. So I'm going to experience a magnetic force down towards the bottom, which is then going to cause that circular path. And that circular path is going to have a radius, and there's going to be some sort of distance from the hole where it entered to where it collides. And this is usually some sort of screen that basically when the electron or proton or whatever hits it, it kind of lights it up, so it can sense when that collision occurs. So we could basically measure the diameter of the circle that is made by that charge as it moves through. So that's kind of how our mass spectrometer works. So how would we find that mass based on this information? So first of all, we know that there is going to be a relationship between the radius here and x. So I can see that x is going to be 2 times my radius. All right, so let's take a look at this particular example. So we have ions that are going to enter a region of constant magnetic field B, perpendicular to the path. The ions follow the semicircle. We have a known x value, because that is one of the values that is often known. We know that it has a single excess charge, in this case a proton. We know the magnitude of the magnetic field strength, and we know the potential difference that the charge is accelerated through. And we want to use that information to find the mass of the ion. So we've already established that our position on the screen that it hits is going to be 2 times the radius. Using our centripetal force equations, we can derive that our radius is mv over qb. We've done that enough. I'm not going to do that again for this particular problem. But we have 2 unknowns. We don't know the mass and we don't know the speed. Our ultimate goal is to find mass. So we need to find a way to figure out what speed these particles are entering that field at. So like I said, one option is a velocity selector, but that's not what we have here. However, we do have a known potential difference that is creating an electric field. So in this case, we're actually going to use conservation of energy to figure out the speed of that charged particle. So I'm going to assume that at the starting position right here, when it leaves, that it's going to start at rest. And it's going to accelerate to some kinetic energy equal to 1/2 mv squared over here. In order to get faster, there has to be a change in potential energy. Well, that change in potential energy is equal to q times my change in velocity. So what I can do is I can set that my change in kinetic energy is equal to negative my change in potential energy. Whatever is gained is lost, right? Delta K is going to be K2 minus K1, and delta U is going to be Q times delta V. My initial kinetic energy is 0, and my K2 is going to be 1/2 mv squared, and that's going to equal negative Q times delta V. Now that delta V is known. It was one of the values they gave us in the problem. So in this case, what we're going to do is we are going to use this equation to solve for my speed. So when I do that, I find that my speed is going to equal the square root of negative 2e delta v over m. I'm using E for Q because it is a single elementary charge, 1.6 times 10 to the negative 19 coulombs. Now, this looks a little weird because we have a negative charge in there. That negative charge is going to make sense when we plug in our potential difference, because we are going from high potential to low potential. So our delta V is actually going to be negative because we're going from low to high that is going to be a negative value. So when we plug in delta V, it's going to be negative. It'll cancel out that negative there for the speed. If you forgot that negative, it wouldn't be the end of the problem. You just probably would also have forgotten that the delta V should be negative, so you would end up with a correct answer. So that negative is not super crucial. You do have to be careful, right here, this kind of popped up, that you're very careful with your capital V's for potential and your lowercase v's for speed. It is very easy to get those confused when you're working. So be very, very careful to make sure those are unique. Sometimes what I do when I'm working with speed, I'll curve my speed and I'll keep my potential kind of capitalized. So I actually use the Greek letter. This is actually the Greek letter nu. So sometimes they'll use nu for speed instead of a V, so I'm not confusing that with potential. So in this example, I have the equations that we need. We knew that X was equal to 2 times R, but R was equal to mv over qb. So substituting that in there, and then we have that our V is equal to square root of negative 2q delta V over m. Now, when I went back to this slide, I didn't substitute an E in this version, so I'm going to leave it as Q here for a second. I'll just substitute the E back in at the end, but it is still one elementary charge. So subbing in, we get that X is equal to 2m over QB times V, which is the square root of negative 2Q delta V over m. So I don't like having that square root in there, especially because my mass is in 2 different locations. So I'm going to square both sides of this equation. So I get x squared is equal to 4m squared over q squared b squared times negative 2q delta v over m. So simplifying down, one of my q's cancels, one of my m's cancels, and I get x squared is equal to negative 8m delta v over qb squared. I can then solve for mass, and my mass is going to equal negative b squared x squared e over 8 delta V. So subbing in for E for that elementary charge. So we have that equation right there. And you can then plug in the values. And plugging in all the values that are given, making sure that they're in SI units. Noticing that right here we have the negative. And then we also have the fact that our potential difference is negative. So those negatives cancel out to give us a positive mass. Negative masses aren't possible. And if you plug in all those numbers, you get a mass of 3.9515 times 10 to the negative 25th kilograms. So what does that tell us? Well, with a little bit more chemistry, we could figure out what this was. So if we convert our mass into AMU, atomic mass units, 1 AMU is 1.66 times 10 to the negative 27th kilograms. And we end up with 238.04 AMU, which would give us a mass that is equivalent to uranium-238. So this would give us the ability to find an unknown mass using electric and magnetic fields. Now we can of course put other particles into magnetic fields to see how they behave. And this was a lot of the experimentation that we did when we first started discovering subatomic particles and different types of radiation and figuring out what are they made of. So if I take some sort of radioactive source and we were to shoot that radiation into a magnetic field, in this case a magnetic field that is into the page, there are different paths that could happen. Some of our radiation can go straight through, some can bend left, some bend right with different radii. So we have the alpha, beta, and gamma radiation. These are different particles that you might encounter in chemistry. You might encounter them here in physics. So Just reminders that an alpha particle is a helium nucleus. It has 2 protons and it has 2 neutrons. So it is going to have a mass that is equal to 4 times the proton. So the mass of alpha is going to be 4 times the mass of a proton. That's because the neutrons and protons, too, like many sig figs, have the same mass. So I don't give you the mass of the neutrons separate because to the 3 sig figs that's listed on your formula sheet, they are the same value. And then the charge of the alpha particle is going to be 2 times the charge of a proton. So it's going to be twice that. So the mass is 4 times that of a proton. The charge is twice that of a proton. Beta is another common radiation source. Beta is essentially an electron that is ejected from the nucleus. So because it's an electron from the nucleus, it actually comes from, it's actually ejected from a neutron, and it converts a neutron into a proton, changing the atomic number of the element. So it's an electron from the nucleus. So therefore, the mass of beta is equal to that of an electron, and the charge of beta is equal to that of an electron. Gamma is just energy. So it has no mass, and it has no charge. So when you look at these different paths of these particles, the magnetic field, which is which, well, gamma is going to pass through undeflected because it doesn't have a charge, so it's not going to be affected by the magnetic fields. If you use your right-hand rule, you can see, like, the helium nucleus, it's positively charged. So if I put my fingers in the direction of the velocity from my radiation source and into the page for my palm, my force on a positive charge is going to be to the left, so my force on a negative charge is going to be to the right. So I can see that that helium nucleus is going to move left, and my beta particle is going to move right. So that alpha is going to go left. Now, also notice that they have different radii, and the different radii is going to be dependent on the fact that they have different charges and mass ratios. So our radius is mv over qb. So assuming that they have the same velocity and magnetic field, the bigger the mass to charge ratio, the larger the radius is going to be. So the mass to charge ratio is going to be much higher on the helium nucleus than it is on the electron. And the same thing is going to be kind of true if you were to look at a proton. So your electron is going to curve quite a bit because it's got a lot of charge for the mass that it has, whereas your protons aren't going to curve as much, and your helium nucleus is going to curve even less. So that gives us the end of kind of the first part of this lesson over magnetic fields and the motion of charged particles. We have more because when we start taking lots of charged particles and moving at once, we get electric current. So we're going to take a look at some additional concepts related to magnetic fields, and then also start taking a look at how those magnetic fields affect currents, not just singular moving charges.